With this video, we're going to look at the atmosphere and introduce the greenhouse effect. So, the atmosphere of the Earth today, made up of several gases. The most common gas is nitrogen. Nitrogen's formula is a diatomic molecule, so it's N2, and it makes up 78% of the air around us. Most people don't realise that nitrogen is the main gas in the air because nitrogen is fairly unreactive. It doesn't really react with anything, so people haven't really heard of it. Oxygen, next most common gas, another diatomic molecule, O2, 21% of the atmosphere. Okay, now those mathematical amongst you will know to 78 and 21 add up to 99. So that's the vast majority of the atmosphere. The other major gases in the 1%, argon is a noble gas, therefore formula Ar. We've got water. I know you're thinking water's a liquid, but of course water evaporates and makes a gas, makes clouds, and that's where the rain comes from. So we've got water in the atmosphere. And we've also, of course, got carbon dioxide. Carbon dioxide, formula CO2, that's the one we've all heard of because of the burning of fossil fuels. H2O, still got the formula, water vapour is still got the form of water, we put a little G after it to make the point that it's a gas if you want. And all these together make 1%. You can draw a pie chart in that hole if you want to. It'd be good if you did, because often you're asked to look at pie charts for the atmosphere when it comes to exam questions. Anyway, next one. Explain why scientists are unable to be precise about how the atmosphere has evolved. And the short answer is the Earth's been in existence for 4.5 billion years, and humans have really only evolved about 20,000 years ago. So the simple answer is there's no scientists alive then. Scientists have to rely on information from secondary sources, indirect sources if you like. E.g. ice cores. Scientists are getting a lot of information from Antarctic ice cores. The ice when it snows in the Antarctic, it just doesn't melt, and it traps bubbles of the atmosphere for when it's snowed, and then next year it snows on top of that. Next year it snows on top of that. So we've got hundreds of thousands of years in some cases of information about old atmosphere by drilling to the very bottom of the ice sheets in the Antarctic, and so we also get information from ancient rocks. Okay, so scientists are unable to be precise because we're getting information from secondary sources like ice cores and rocks. You need to know a chemical test for oxygen. It's very simply, it's you put a glowing splint in the glass. So you light a splint and blow it out, so it's just glowing orange. Glowing splint, and then if it's oxygen, it relights. Just one of the gas tests we need to know. All right, next question. Which gases are responsible for the greenhouse effect? In your book, there's a whole bit of writing above that tells you all about that, but we'll just quickly skip to the answers now. The gases responsible for the greenhouse effect, number one, the one you've probably heard of, carbon dioxide. Okay, the second one you may have heard of is methane from cattle farming. And the third one you probably are not aware of, but does have a massive impact, is water vapour. Okay, on a cloudy night, it's often a lot warmer. When there's no clouds in the sky, you often get frosts. In the winter months, certainly. Describe how the gases responsible for the greenhouse effect heat up the atmosphere. Okay, well, these greenhouse gases mentioned above, the carbon dioxide, the methane, the water vapour, the greenhouse gases absorb infrared radiation from the sun. So instead of when the sun sets at night and that infrared radiation, that heat radiation escaping the planet, these gases have absorbed it and keep it in, thus warming the planet up. It's kind of like when you pull a duvet over yourself at night. If you pull a thin summer duvet over yourself, some of your heat escapes. If you pull a winter duvet over yourself, and lots more heat stays in. Well, this carbon dioxide, the water vapour, and the methane, that's like a winter duvet of an atmosphere. They absorb much more infrared radiation. So the greenhouse gases absorb infrared radiation from the sun, and this heats the planet up. Okay, it's the very basics of the greenhouse effect. So, what is the human race doing that leads to an increase in the greenhouse effect? Number one, burning fossil fuels. Coal, oil and gas. We dig them out of the ground. They're carbon-based fuels. When we burn them, they react with oxygen, thus making carbon dioxide. Two, cattle farming particularly, but any type of animal farming. That is having a large impact on the greenhouse effect. We are also deforestation. We're chopping down large parts of the rainforest. That doesn't add carbon dioxide. Let's just write that in brackets. Doesn't add carbon dioxide. Okay, just stops the planets from processing it. And that's quite important. So there's three things doing there that we're adding to carbon. We're doing to add to the greenhouse effects. Obviously, animals respire, take in oxygen, give out carbon dioxide, but we're going to do that anyway. These are the main ones that are adding to that greenhouse effect. So this graph here, it's not really on the specification, but I just think it's great evidence for the greenhouse effect. I mean, you hear lots of politicians talking about the greenhouse effect and how maybe it does or doesn't exist. You know, Donald Trump was certainly in news last week for saying, you know, there's a lot of scaremongers out there. So what's the science behind it? Well, this is information I first came across at the British Antarctic Survey in Cambridge. And they're doing a lot of information, a lot of research on climate change. And this is data taken from ice cores. So the blue line on the graph here is how the carbon dioxide in the atmosphere has changed over the last 400,000 years. So this is today here, at this end of the graph. And this is going back into ancient history. Now, the interesting thing is humans really only evolved, I mean, if you think about 2,000 years ago, back to zero sort of BC AD sort of thing, that's about, that's 50,000, that's about there on the graph, isn't it? So the Industrial Revolution, we started burning coal, is about there on the graph. So the good thing about this graph is it shows the atmosphere, okay, before humans got their dirty little hands on it. Before humans. And look how the carbon dioxide levels have naturally gone up and down on the planet. So that's the blue line is carbon dioxide. Now the red line is also the global temperature. Okay, so you can see things like ice ages on this graph when the planet was exceptionally cold. Okay, and again, the planet temperature has gone up and down before humans got their dirty little hands on the planet and started changing it. And this is evidence that a lot of climate change naysayers, people don't agree in the climate change or say it's not a problem or we don't need to worry about it too much. This is the evidence that they will often cite. They say before humans started impacting on the planet, the amount of carbon dioxide and the temperature naturally varied. And they're absolutely right, of course. The trouble is that they're picking part of the graph to explain. And here's the reason why people like scientists at the British Antarctic Survey say, actually, we do need to be concerned about this. Because what you notice about these two lines is they have tracked each other for the last 400,000 years. As the amount of carbon dioxide goes down, so does the temperature. As the amount of carbon dioxide increases, so does the temperature. Okay, and apart from the odd issue on the graph, and maybe there's reasons for that, like volcanic eruptions or dust clouds or asteroid strikes or whatever else. Apart from the odd blip on the graph, that is the case for the last 400,000 years. Now let's consider today, and this is why scientists say we need to be worried, because the carbon dioxide parts per million scale starts at 170 and is at 290 here. Okay, so the amount of carbon dioxide in the last 400,000 years has never gone above 290. Now, when I was at school, I remember my biology teacher, Mr. Phillips, telling me that the amount of carbon dioxide in the atmosphere was 300 parts per million, so already high, and that's back in the mid-80s. Well, today, the amount of carbon dioxide in the atmosphere is about up here, about 400. So we need to expand this graph. Okay, so this blue line needs to go like this right now. Okay, now it doesn't do this on this graph because this hasn't hit the ice cores yet. Okay, because this is all very, very recent. So this, now we've got on the graph the amount of carbon dioxide and the temperature radically different. I mean, look at the difference there to there. It's never anywhere near apart on the graph like that. So what scientists at the British Antarctic Survey and other scientists around the world say, the only thing, what this graph shows almost conclusively, is the only thing that can happen to global temperatures at this point now is they will rise to match the amount of carbon dioxide in the atmosphere. Because the carbon dioxide, of course, stores the infrared heat radiation from sun, so the planet will heat up. And the only thing they're in doubt about is how much the planet will heat up by. And that is why a lot of the politicians around the world are saying we need to do something about global warming. And I'm sure that will happen. That's the hope anyway. And that's the basics of the atmosphere and global warming.